Hello, everyone. Types 5 and 6 of the uniform acceleration questions coming at you. All right, so we looked at types 1, 2, 3, 4 so far. I put 3 and 4 down here just to number things, organize things logically here. Type 5, we're going to look at being given the initial and final velocities and the acceleration. Obviously, we're going to be able to get the time directly with the normal acceleration equation, and then kind of the bonus of the delta d. So similar flavor to 1, 2, and 3. I almost wonder if that should be type 4, to be honest, just in sequencing, but it doesn't matter, of course. And then in type 6, we're going to be given the final velocity, the displacement, the time, and we're asked to get the acceleration and initial velocity from that one. So that one's a little bit different. So here we go. Type 5 question here for you. So car accelerates at 2 meters per second squared, increases its velocity from 10 meters per second to 50 meters per second. Determine how far the car traveled while speeding up and how long that took. So pull out the given information. Could have had the acceleration first, I suppose, in the list since it was said first. Initial velocity of 10, final velocity of 50, asking for time and displacement. So that's the question all set up for us. So let's go through this. I'll just reveal stuff as I go here. The VT graph should be pretty easy. Starting at 10, increasing to 50, right? And you'll be able to label or illustrate on the graph that you know the acceleration. So starting at 10, ending up at 50, nice straight line because it's uniform acceleration. The 20 number would just get put in there later once you know it. But for now, the 2 meters per second squared is known information. And you can point out while we're at it on here pretty easily that you know that the delta V is 40. Okay. So when you're looking at what you can do first in this question, since we have the acceleration information, it's certainly going to make sense to use that one first. Right? So that probably says first here. So we just plug numbers in, and notice that I'm just using that calculated delta V, or I could have put in V2 minus V1. Doesn't matter. We can calculate out the time nice and easily. And then for after that, the area giving us the displacement, nice and easy as well. We can just plug numbers in, right? We've got our rectangle and our triangle, and we have the time is now 20. And so, we have the length times the width, the 20 times the 10, and we have 1/2 of that 20 times the 40. Okay, so easy peasy, really. Travel 600 meters during that 20-second interval, and so on and so on. Okay, so I think that should seem very doable with the VT graph method. No problems. In the next step here, let's see what it looks like using equations. Okay, so notice we had to do displacement second. So to flex the power of the equations here, let's pick an equation that'll work to give us displacement directly. So to do that, we can easily just analyze what we have, which is V1 and V2, acceleration, and we're going to work to get displacement directly. And so you can tell this equation will work nicely for us. All right, so we're going to use that equation, and we're going to plug stuff into it. So the 10 is going to go in and get squared. The 50 is going to go in here and get squared twice times the 2, and then the unknown delta D, right? So squaring stuff, subtracting from both sides to solve, dividing both sides by 4, boom, you get your displacement 600 meters. Hey, look at that, same number. Imagine that, right? Then the next one here, if we're looking for the time, so we can go ahead and get the time. I think that one's going to be pretty straightforward, right? But let's just do our normal selection. Yeah, it will be. Let's just do our normal selection process, though. But I think you should really notice here that we're really just talking about an acceleration question, like the original stuff we started to do, right? When we talked about acceleration as a concept originally. So it's just going to be your basic acceleration equals delta V over delta T equation. Same as before. All right. So a slowing down case. I said I was going to leave this as homework in the past here. Maybe I'll do this one with you just to give extra help as we go through this. So let's do that with VT graph first. So let's make that obvious. Let's do this VT graph method. All right, VT graph method. So of course we'll do a VT graph. Let's do that up here, nice and easy. Out of the way here. So we need to have V and T labeled, and so initial velocity of. Don't worry about that green arrow there. I was just basically showing the idea that things are not the opposite way, like we're slowing down this time, right? So initial velocity of 50 up here. Get out of the way there, and slowing down to 10. So you can make them be relatively to scale if you want. And yeah, so it looks like we've got our spots, and we know that it's uniform acceleration because the kind of questions we're doing. So it's a nice straight line, and we can list the acceleration on here however you want, really. Acceleration equals the -2 meters per second squared. And so this would have been a similar story, but it would have just been a car is slowing down at a rate of 2 meters per second squared and so on, right? So picture of the story would have that embedded into it. And so because it said slowing down from these forward directions, that would be a negative and so on. Okay. So that's about it on that. I guess maybe I might just sort of put this down and point out that there's a delta t here that's missing that we're going to get. And then you could also point out delta d equals the area, and we don't know it as well. Okay. So yeah, so I think I would go ahead and start with acceleration slope concept. This one, of course. So we have acceleration equals delta v over delta t. And so we can start putting things in. We've got our -2, and we can put in our v2 minus v1. Our -2, and we'd have v2 minus v1. So it'd be the 10, take away the 50. We'd have a time interval. And work towards solving for. So we've got our -2, we've got our -40, we've got our time. And so we just have to solve for that variable on the bottom. We do that by multiplying both sides by time. Gives us a -2 delta t over here equals a -40. So we divide both sides by -2. End up with the time being 20. It takes 20 seconds to do this. Therefore, 20 seconds, blah, 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 right? So that is our time. And then using that information, we get our displacement equals the areas and so on. So I guess our triangle looks kind of like that this time, right? Looking at it here, we've got a triangle that's shaped like that, and they oriented that way or whatever. And so displacement, we're just going to figure this all out. We have a length times a width. We know this is 20, just like before. Well, I was going to say just like before, but I mean, it's a slightly different question. But yeah, so the 20, notice the difference here is it's times the 10 this time. And 1/2 of the base times the height. Height in this case is the 40. And notice this is important because I'm going to be relying on you recognizing this later on. Technically, delta v equals -40, right? But as a height of a triangle, height of a triangle for representing positive displacements forward and so on, we just put that as a positive value. So yeah, height is positive for positive displacement. So I'm going to introduce something to you here so that it makes sense later in the lesson. But really, if you think about it, that positive 40 really is negative delta v, isn't it? Right? So in other words, it's negative of -40, right? Equals the positive 40. So if you think of what's there, that's actually a negative delta v, and that's going to be important later on in this lesson. So trying to help get us there. So we've got the 20 times the 10, we've got the 200, we've got half of 20 is 10, 10 times the 40 is 400, and so we're getting 600 meters. So therefore, travel 600 meters, takes 20 seconds to do that, and so on. Right? So there's just the VT graph method of it. And let's grab UASM. Catching on for you guys yet? There we go. And let's grab the question. 5, slowing down. Go. Equations, of course, you can tell because you got the selection sheet there. So doing the same work, but just seeing what we get from equations and so on. So we had to do displacement last. Let's do it first this time just to show that we have the power of the equations available to us. So here we go. We've got these. So initial and final velocities. I normally just circle one than the other, but accelerations. And we want displacement directly. So fancy equation kicking in. There's some extra power built into that equation. That's why it comes up in these cases. So V final or V2, I had it listed as V2 there, so I'll stick with that. V2 squared equals V1 squared plus twice acceleration delta D. And so we've got our 10 squared, we've got our 50 squared, plus twice our acceleration value of -2 and our displacement value we're looking for. So we've got just 100 and then a 2500, then a -4 delta D. So let's just subtract both sides, obviously here, 2500. Oops, that's supposed to say 2500. And end up with -2400 equals the -4. And of course, then divide that and you're going to get the 600 that we had before, right? We had 600 as an answer. So that gives us the 600 meters, confirm. That's victory slashes in math, in science land. But yeah, therefore, 600 meters as it was before. Question just done this way. And if I wanted the time, I think we can skip that one really, but acceleration equals delta V over delta T. It's just the -2 equals the delta V. So V2 minus V1 is 10 minus 50, giving us the -40, and the time we just solve out like before, right? So we end up with 20 seconds as before as well. All right, so type 5 working for us, I think. Moving on to type 6. Okay, so first one of seeing type 6. This car takes 5 seconds to speed up to a final velocity of 20 meters per second while traveling 60 meters. So we're given a time, final velocity, and a displacement. Given a time, final velocity, and a displacement, right? Type 6. Find my slide here, okay? So there we go. There's the given information. So this one's ready to go for us. I'll just reveal. So we're starting at ending up with a velocity of 20, right? So ending up at a velocity of 20 up here, starting at some smaller number, right? That apparently ends up being 4 later on. We'll show you. We'll put that in there once we've calculated it. And so this is my delta V here, V2 minus V1, and so on, right? That's going to, again, come up soon. So because we have displacement, we're going to use it. So displacement equals the areas. We're going to have a 5 times a V1. So it's a little alarming that we don't know the V1, but just put it in as V1, right? 1/2 of the base, the 5, times the delta V. Again, here that's like an extra variable, and so you have to put it in terms of what you know, right? Delta V equals V2 minus V1. Put it in as 20 minus V1, like that. And just work out the solving for V1 now, right? Have to expand out, collect like terms, just like in math class. So multiplication across is going to give us a 50 minus a 2.5 V1. collect those, have only 2.5 v1s, and then take away 50 from both sides and divide both sides, you get this initial velocity of 4. Okay. After that, of course, you have v1, v2, and time, so you can get acceleration dead easy, right? So you've got the delta v over delta t essentially going on there. Okay, so that's the VT graph method for type 6. Obviously, no major issues there. There's a bit of an issue with this one in the slowing down case. Okay, but I'll show it to you, and you'll just hopefully still sort of gain from the extra understanding you get from visualizing this stuff, right? I might not ask on a test for this one to be done this with the slowing down case, right? So let's get towards the slowing down case and see some of the issues, okay? So a slowing down case, I might just on a test just say, you know, do it by equations, right? Because I wouldn't want you to get tripped up by the weird little detail of the delta V value. But this delta V value here is positive, and so there's no issue. Soon you're going to see a delta V value that's negative, where there would be an issue unless you deal with it properly. So question is, could this question have been a slowing down case? So could it have been read as a car takes 5 seconds to reach a final velocity, in which case it could be speeding up or slowing down? You don't know. And so if you look at the numbers of this, if we were starting from a faster velocity and slowing down to that in the 5 seconds, you would already have traveled 100 meters. So you would have gone further than the overall displacement, right? So, you know, you would have been traveling 100 meters plus even some more here. And so clearly you can't have 100 plus something is 60, right? So you tell that just can't be true, right? But you know, what would the math result be that might lead to? Sometimes in math you get like roots of negatives, right? In this case, I think it's something else, so we'll see. Okay, so let's just let's incorrectly assume it was slowing down. Okay, so we're going to say, okay, we've got this situation here, right? We've got displacement equals rectangle plus triangle. And so we start to just put the numbers in. We have the 5 times the 20. That's apparently our final velocity now as we're assuming things, right? And oh, the other one's bigger than that, I should say, whereas before it was the top one, right? Yeah. And then what do we have next? So this delta V, there's an issue here, right? That delta V would represent a negative number. And so really negative of that is needed for a positive height. And so when we look at delta V is equal to, let's do this actually up here. So delta V here, right? Delta V equals V2 minus V1. Get this out of the way. And so delta V is really 20 take away a V1, right? But that is a negative, right? It's this arrow down, right? So this is a negative. It's not obvious that it's negative because it totally depends on the values of V1, right? But we know based on the situation that it's negative. And so if I put 20 minus V1 in for this, that would be wrong. I'd be putting in a negative height even though we're going forward. And so this, I'd have to put it in as negative of V1. So negative of the 20 minus the V1. I'm really just showing you that this works as long as you're careful with this height situation. So this is the equivalent of putting in a positive number instead of a negative number, right? Algebraically, it looks weird. It does represent a positive now. So this is what we get. Multiplying that out, we get what? A minus 40 from taking the 100 away, a minus 50 from that, plus 2.5 V1. Then we add 50 to both sides. We divide both sides by 2.5, and we end up with an answer of 4, which, if you think about it, it's like we're saying that the answer is 4. Well, that can't be the case, right? So if you look at up here, that can't be 4. It can't, like, that's, like, you can't decrease from 4 down to 20. It just doesn't make sense. So right now I'm saying, like, you know, that's not greater than 10, so clearly there's a wrong assumption. Well, it's kind of amazing that this wrong assumption still led to the correct conclusion. You're like, oh, so i.e. we were actually speeding up, right? It was really, come on, catch up here, really a a speeding up case. Up case. Reality. My smart board's chugging. All right. So we know it's like we're seeing that it's actually a speeding up case just by making the assumption we did and seeing that it doesn't work out. I'm just gonna save here in case it crashes on me. So then if with equations, right? If I say, okay, let's assume that it's slowing down with equations, we're not even really doing anything here though. You'll see in a second. But basically we choose the equation. So we're like, okay, this is the equation we need to use. And so we plug the numbers in and we, multiply both sides by 2, divide both sides by 5, end up with 24 equals this and so on. And we solve and we get the 4 still. That's the same as we got. So the answer is like, oh, geez, it's not greater than 10 and so on. This actually, again, tells you that you're actually speeding up from 4. So I'm going to cross this little assumption thing out here and say, well, really, this is just my page for determining the initial velocity using equations. That's all that really is. Okay? So we determine the initial velocity using equations, whereas before we determined the initial velocity using VT graphs, right? All right, so let me get back to where I was here. If we wanted to get acceleration directly, instead of getting V1 and then getting acceleration, with the equations, of course, we can get it directly. So let's pick an equation for that. So we have V2, we have displacement, we have time, and we're looking for acceleration. Let's just use the equation that has all that stuff in it. So this is the one right here. V2 delta t minus 1/2 acceleration delta t squared. So boom, there it is. Boom, the numbers go in. And then math leads to the solving of the answer. So if you need help with those math steps at this point, just reach out for some help. But obviously, I'm just going to collect like terms and solve out for acceleration. It gives us 3.2 meters per second squared in this case. So did I have? Here, type 6. Yeah, 3.2. That's the same as I had before. There we go. So that's working nicely. This one here, if you're told it's slowing down, right? It's a slowing down case, obviously the numbers work out properly. So I'm just gonna, that's all worked out for you if you wanted to go through it as well. So this is the equation version of things for this question. I better take a second here to show this, right? So basically we're saying we're ending up with a final velocity of 4d, having slowed down to that, right? We're traveling 200 meters. It takes us 4 seconds to do this. We want to know the initial velocity and the acceleration. So we did that. We figured out, we started with 60 and we had an acceleration of 5, right? Slowing down at a rate of 5. So that's the equation work. Like we know it works, right? Again, I just want to show a little bit more about that negative delta V thing. Okay, if we did this with a VT graph, see how this just helps you see things a little better too. That VT graph, we're starting with an unknown velocity, slowing to 40. Right? It's certainly easy for me to point to and talk about. So this, I don't think we need that. So that delta V is a negative value. Okay, so we got to watch for that, right? So I should be able to get. I'm trying to solve for V1, right? So we should be able to get that same answer for V1 here of 60, okay? So that's what we're thinking we're looking for, right? So we're working with the displacement. Obviously gonna have a 4 times a 40, right? 4 times a 40, and then a 1/2 of a, base times a height, the delta V, but we know that delta V is actually a negative. We need the positive version of this stuff, right? So we need the 40 minus V1 with the negative of that. So it's negative of a negative thing, right? So it really becomes that. Minus 40 plus V1 and then rearrange it. Look nice, right? So that's why I'm gonna have that in there as V1 minus 40. And just some algebra here. Take away 160 from both sides, multiply those out. Multiply that with a 2, I guess, first, and then onto it. So we have 2V1 and so on, right? Looks like I didn't get rid of the 160 yet. Instead, I combined the 160 with the 80. and then took away the 80 from both sides and divided both sides by 2, and it worked. We got the 60, but it wouldn't work if you didn't correctly put in this as the proper positive number. Okay, so this slide just shows that if you messed up the idea and put this as a negative value, it gives us an answer of 20. So you're like, wait a minute, I can't slow down from 20 and end up at 40. So this would actually be an error. This wouldn't be a correct solution to anything. Okay, so doable by VT graphs still, but that extra trick. So really, VT graphs starting to show their worth more and more as we go through this, of course. Okay, so that's it for that. There's only 4 questions here, so I think I have a speeding up and a slowing down, one of each case. So that's a very reasonable amount to practice, and if you need more practice, I think I'll release the sheets that I've been pulling these from soon, actually, so you have a chance to do more practice if needed, but that's certainly not the concern most people seem to have at this point. But yeah, so anyways, I'll leave it at that. All right, thanks for watching.